Well, hi, good morning. Thanks so much for joining me in my shop here on August 12th. Oh my gosh, it's almost halfway through August. Yikes. Well, so the last, I don't know, 7 or 10 days I've been working on various pieces of equipment. Let's get back to working on a radio. Here's an old beater that I've acquired. I didn't go looking for this radio. This radio is basically handed to me. So what we're going to do is we're going to check it out and see about operating it. So it looks like there's an antenna bolted to the chassis here. I'm going to take this little screw out. So the weather here, you know, I am Canadian, so Canadians like to spend a lot of time talking about the weather. So that's why I talk about the weather here. So the weather today is gray, rainy, kind of ugly. So there we are. So that's why I'm in here. It's pretty much coming off its form. So this radio has a corner shape to it here. These things often get into trouble because of people sticking their fingers through them, deforming them. This one's deformed in this area. Cloth is a little worn here. Gives it an old ratty look. All these curved shapes in there. Let's see. Yeah, it's a very light radio, so I suspect it's just a 5-tube radio, but it seems to have a short wave band on it. Or does it? Bands. Oh yeah, broadcast and short wave. So it's a 2-bander. But it's so light, it feels like it does not have a transformer. Okay. So the cabinet looks and feels solid, but it's really pretty beat up at the top here. Pretty beat up. But the plastic cover here looks good, and the radio in behind looks good. 3 screws holding it together. Let's pull the insides out. It's got a couple. Something unusual going on there, I think. Okay, let's pull it out. That's pretty loose. What's going on with that? That's the tuning. Awfully loose, but working. If I take these other ones out, the radio's going to drop. So I'm going to catch it. Bits and pieces. Looks like mouse turds coming out of this. I think it's mouse turds everywhere. Metal bottom plate. Oh yeah. The mouse has been living in here somewhere. Oh, it's just covered. Oh my gosh. It's in horrible condition. The capacitor's got crap all in it. This looks like this has been gnawed on, chewed. All kinds of bits and pieces down there. Oh my gosh, this is bad news. This is really bad. Very heavy rust here. What's this from? Water getting into the radio, or is that from animal urine? Ooh. This guy's a real mess. Look at the rust on top of this. So this guy's pretty much been underwater. Well, not really, but may as well have been underwater. This is all rusted here too. There'll be a steel piece in contact with aluminum, and you get a poultice of dirt on here, a little bit of moisture, or some amount of moisture, maybe a very humid location or something, and you get the rust starting on the steel. Wow. Do we plug this guy in and try him? Well, it's all up on top here. You know, it's not underneath. Well, I don't know what's underneath yet. It's got all its tubes. So this was owned by a radio guy. So somebody, I guess, a little bit like me. How is this bottom plate held on? This screw here. Something's held on with a little one of these. There's another one here. Looks like there was a bunch, and it ended up going back together with just a couple. Really only this one here, and the screw. I'm sure that screw's got to come out of there. How do you get these things out? Call upon the Nordic fish knife. The Nordic fish knife wins the day. Holding it on here. Oops, another thing just popped out. Another one. I didn't see them. I guess they were rusted and I couldn't see them. They just popped right out. You put a little pressure. What is holding this thing on here? Nothing at all. Well, I'm going to have to clean up in here because I can't work with all this rat turds all over my bench. So we're going to have to stop. But there's a look. Nobody's done anything to this guy. It's amazing though how good it can look inside. It looks like this on the top. I have to pull out all the tubes and really go at this thing. Clean her all up. What a mess. Well, it's probably salvageable though. That's what I'm going to try to do. But first, I'm going to wash my hands and drink some coffee. Well, we just got hit by a very powerful storm. So here's where I live, right here, Aurelia, and Powie. Of course, this is 10-15 minutes behind, so this storm is now just beyond Aurelia. But lots of lightning in this storm, and the result of that is I got a couple of cowering cats in here. Wow, lightning and thunder, of course. Okay, back to the radio. Once this storm is over and I collect myself, I get excited when these big storms come through. Okay, storm is largely passed, so let's carry on here. And the power stayed on, which is good. Oh, I haven't cleaned this up yet. I got so distracted. Okay, let's stop. Stop. There's rat turd on my bench. Okay, that's a little better now. Dusted this guy off. So, should we try running this radio as it stands? What might happen that would be terrible? Nothing really. First of all, there is no transformer. I was right. There's no power transformer in here. So it's your basic 5-tube radio. 1, 2, 3, 4, 8, 5 tubes. 5-tube radio, but short wave, which is just a little bit unusual. Not terribly unusual. Some adjustments here. Antenna it's loose, but it seems to be intact. Everything seems okay in that respect. So a little worried about the chewing in here. It may have chewed through a wire. That wouldn't be very good. So the reason for wanting to operate this, there's still more crap coming out of it, is to find out if there's any really major problem with it. Some part that can't be dealt with. You know, not always possible to figure that out ahead of time, but you really don't want to find out after 3 or 4 hours of work that the IF transformer is shot or something like that. I mean, a radio in this kind of shape, really, how far do you really want to go with it? I mean, any radio can be fixed. It's just a question of time, effort, expense, and things like that. Well, I guess if you ran this over with a truck. Okay, maybe not in that case, but I think we should plug it in. I think we should plug it in because I have safe ways of doing this. Cord's in great shape. It looks like somebody must have replaced it. Okay, we're going to plug in here. I'm going to rely on some dim lights over there. As soon as I set this where I want it, right there. So the power that's going to get to this radio is going to go through a couple light bulbs back here. And they're both screwed in. I'm going to unscrew one of them. Okay. So that's a fairly heavy restriction. A small radio like this drawing a small amount of power is still going to end up getting most of the line voltage, even with a light bulb right in series with it. So now, what do I need to be prepared for? Smoke and flames. So I need to be able to cut the power. Smoke and flames on my wooden bench. Volume is here. Band switch is here. So put it on AM. And tuning is here. We'll tune it to the low end of the band here. Okay, Mr. Radio, can you work? I put the tube back in. Yep. Okay, so here we go. First, we check it, make sure it turns off on its own. So I'm now applying voltage to the cord. 108 volts. A little low. Let's just put it up here a little bit. Okay, 115. When I turn the radio on, or when I apply power to it with the radio on, this voltage won't be 115. It's going to drop down to probably around 95. That would be my guess. So we cut the power, put on here, got a light that's going to come on. This is essentially another dim bulb in a way. Not really. This one will behave kind of the same way these lights will behave. If this radio is in good shape, we may see this light come on and go down and then come up again. As it comes up again, you may hear the radio start playing. Or I may be running for the fire extinguisher. So I'm going to turn the radio on now and put the volume up 30% or so. My guess is we're just going to hear a big hum. Here we go. dimming down. It's going to come up again. Dimming down, down, still going down. Voltage 90, 98, 99, 100. That's more than enough to make a radio like this operate. .91 volts. Well, it sounds like it's operating. Let's check the volume control. Okay. Tune the radio. So that sound is a interference sound I hear in my shop all the time. So this radio is receiving, not receiving a station though. I bet you it will. Somewhere. Station there. So this is probably 590 right here. That's the strongest station in my area. If we turn the radio, we may get better reception. So you hear the lightning. Sounds like I'm just adding noise when I do that. Well, okay. So what this proves is an awful lot. Yeah, it's humming and buzzing a bit, and the reception is poor and all that kind of stuff. But the speaker works. The speaker transformer's working. The two IF transformers are working. The radio can be tuned. It's able to pick stuff up, so all the tubes are working. May not be working perfectly, but they're working good enough. The antenna is connected and operating properly. So it's really, surprisingly enough, electronically, it's not in bad shape. Chances are, I'm going to pull the plug. Chances are, if I go ahead, basically get rid of all these wax capacitors here. 1, 2, 3, 4, 5, 6, 7, 8 of them. And this big filter capacitor here. This radio will probably work pretty good. That's my guess. As good as it could work, really. Out the back here is a wire where you'd hook up your shortwave antenna. It's cut right off for some reason. Good show. I think I'm just gonna take a little break here and ponder. As you may or may not know, I always prefer the fun way of doing things. I think maybe it might be interesting to poke around with a voltmeter in here a little bit. In particular, hunt down the grid to the output tube and see what's going on the grid. It should have a negative voltage on it. Does it really? Plus, I should be looking for a schematic. This is a Moffat's, M-O-F-F-A-T-S. I've never heard of that. Moffat's, made in Weston, Ontario, not too far from here. And it's got a model number, G2465. So maybe I can hunt down a schematic for it, which would be really helpful. I should do that right now, in fact. Yeah, I think I'm gonna. Let's go hunting for the schematic here first. Well, here it is, G2465. The interesting thing is, This is a Crosley radio. But look what it says here. For model G2465 Crosley Radio and Television Limited, Toronto, and Moffat, Ontario. Moffat. So I looked for Moffat on the map. I don't think it's a place. It's the name of the company. So I don't quite understand this. I don't know what's going on with the radio because it says Moffat. But here's the schematic here. It's upside down. Crosley. Wow, look at this radio. That's pretty nice looking. Well, it's all fixed up. But look what it says here. Grill cloth not original. Yeah. Wow, can I make mine look like that? You know, I'm not a cabinet refinisher, but I'm sure I can clean it up and make it look much better. Okay, well that's good. We've got the schematic here. We've got two schematics. What's the difference here? Can we tell? So I'm looking here at how the speaker is shown in this area of the schematic. It looks the same. Speaker shown in this area of the schematic. This is a nicer looking version of it. So I'm going to download this. We're going to study it a little bit. Okay, here we are. Yep, Crosley G2465. So I think a couple areas that are worth looking at right away is the power supply, and most importantly, how the plug is handled. So we can see one wire from the plug. The plug is non-polarized. It's going straight to this wire. And we can call this the B minus. That goes all the way around the schematic here to this point. And it's connected into various areas. So this is interesting too. So this is going to be a wire in the radio, basically, or a set of wires. There's a capacitor connecting to the chassis. Now, is that what they're trying to say here? What are they trying to say here? Chassis, ground. I don't know what they mean by this. But here we can see there's a capacitor standing between the metal chassis. I have to assume this is the chassis. That's a bit of an assumption. We got to find this capacitor. Improve that it's connected this way. That the chassis is not connected directly to the incoming plug. That's what I want to know, which way it is. Look at the antenna here a little bit too. This is a double band radio. The loop antenna is only useful for the broadcast band. So when you switch over, yes, this is the switch here. When you switch over, you'll be switching to a long wire. That's what this is representing. This is not a big fuse here. This is supposed to be the antenna. Wire hanging out the back or represent the antenna. They should put a little antenna symbol on it. So you would hook up your shortwave antenna and it would feed into here. So you notice this loop antenna has a pickup turn right here, which is then connected to the antenna transformer. And then it has this part out here. So these antennas at a glance look the same, but they're often handled in different ways. Now, this looks like a trimmer capacitor, so you're trimming the tuning of this loop. But the radio itself is listening to this little piece of wire here, smaller loop, that's inside the bigger loop. Very good. Okay, so even with shortwave, you're going through the transformer here, and from there, this is grid. This is selecting what is hooked up to the grid of the first two. So it's either the loop antenna. Wait a minute. This is the outside of the big loop. So the outside loop. So this transformer is only used on shortwave. Why do they have it go up like this? are they trying to show here? Well, it's possible what they've done is, in case you don't bother hooking up an external wire antenna, you can still get a little bit off of this one. It seems pretty poor to me though. But maybe if you had a really strong shortwave station, you could hear it off of this arrangement. I doubt it. I doubt it very much. Today there's too much noise in the air. I don't know. I don't know why they did it like that. But anyway, a larger coil here, which is tuned with this trimmer, is connected to the grid. A big 1 meg resistor here. I'm looking to see how the AVC is handled. So you see this great big resistor here. These are all this is a very common way of doing this. So we go down here. This is the detector tube. We have a RF coming out of this transformer. It gets rectified right here. You can see these two connections here are going to diodes. PD must mean diode. So it's rectified. The rectified result is a DC voltage and a recoverable audio signal. The DC voltage is sitting on this line. We'll go through this resistor like it's not here because there's no current flow in this part of the radio circuit. Exactly what's going on here with all these capacitors. If we look at the tuning, this 6A is the tuning capacitor, and its brother is down here, 6B. 6A appears to have no trimmer, although maybe this is going to do it. I don't know. Looking too far ahead now. We have two oscillator coils down here for the local oscillator, depending upon which band you're on. 22, does that say 22 megohms? No, in this radio the M means 1,000. It's French for mille, M-I-L-L-E, I think. And it's common in old schematics. So if they wanted it to be megohm, they write the word meg. Meg. So you know it's megohms. So you don't want to be fooled by that. Okay, so another thing of interest here is what are they doing about the grid on the output tube? Whoops. Grid on the output tube is getting its signal from the plate circuit of the audio amplifier here, but there's going to be some voltage here, not a lot. I mean, this whole radio is running, the highest voltage it's going to have in it is about 120, 130. This is probably around 60 or 70 volts here. Nevertheless, if it wasn't for this capacitor, you'd be putting 60 or 70 positive volts right on the grid of this tube. Oop, that wouldn't go well. So this capacitor's job is to pass the signal, but block the 60 or, oh jeepers, I got a heavy finger today on my mouse. But block the DC that's sitting here. Old capacitors start to leak. The leaks are very, very small amount of charge, but it won't take much charge to pump up the voltage on this line. You can see a very large resistor here, 500,000 ohms. So a small trickle through here, and this grid will be pushed from its proper negative bias voltage up. It's become more and more negative. Now wait a minute, how is this getting biased? So we'll look at the cathode, KKKK. We see a 150 ohm resistor. Wow, that's a far cry from this big one. This is a small one. And that's, here goes my finger again. And this is going to be a resistor whose job is to push the cathode voltage up. There's a bit of a voltage drop in this resistor. Makes the cathode go a little bit positive. So the relative voltage between the cathode, now a little bit positive, and the grid makes the grid look negative relative to the cathode. So that's the biasing. So this is called cathode biasing. Now normally you don't want the signal going through this resistor because it's a waste of signal strength. So what is commonly done is it's bypassed. So here's a big capacitor, 20 microfarad capacitor, that's big. And that's to basically provide a ground right in here. Then you see the output. So this capacitor, which is connected between the plate and the cathode, is probably there to quell oscillations, drain any RF that might still be around. But it should just be audio here. Audio through the transformer and right into the power supply. So the plate gets its voltage from here and supplied through the windings here. The transformer essentially blocks DC, only AC on this side, and there you are. Permanent magnet speaker making lovely sounds like we heard earlier. Look at this lineup of tubes. The rectifier is a 35. These added as 36. Add those together, you get 70. Add 50, you get 120. So this radio ideally wants to run with 120 volts. To run it with a little less, all these are going to be just a little low. A little bit shouldn't hurt. Now, the heaters are here and here, these two H's. But look at the light bulb. The light bulb is hooked up to T. T stands for tap, and it's a heater tap. Now, there's stories about these light bulbs, and they're there to protect the tube in some way. I'm not so sure that's really true. I don't know for sure. But the problem with this radio is you can't find 6 or 7 volts to run a little light bulb. It doesn't exist in the radio. So to make it exist, they place a tap on the heater here. So this heater's got 35 volts across it. It's tapped not in the middle, it's tapped on one side to generate roughly 6 or 7 volts, something of that sort. And that's where this light gets its power from. That's why it does funny things. When you first turn on the radio, it gets bright, then it's dull, then it's bright again. Another thing is, I don't know about this one, some of the plate current that's flowing in these tubes can flow through this light, but I don't know about that. I sort of know about that. Not enough to talk about. Band change switch shown in broadcast position. Good. Okay, so it's nothing terribly unusual about this. We need to find this capacitor. We need to test this grid for its voltage. We need to find this capacitor. This guy first. Let's find this one. One end will be soldered to the chassis. It'll be the only one like that in the radio. Let's go looking. Go looking we will go. We'll see if we can spot it. So looking for now where's the cord? So the power cord's coming in up here. Chances are that capacitor is up here too. Power cord. Another thing I can look for in here are there any other connections onto the chassis other than the one I'm looking for? So are there terminals coming up from the chassis? Some of those terminals can be associated right with the tube sockets, in fact. And I don't see anything connected to the chassis. Here. Look at this capacitor. Nope. This capacitor's hooked up to this post. We got one hiding under here. I see a terminal strip down here. The terminal strip is bound to be attached to the chassis. I see 2 capacitors connected to the terminal strip. And it looks like the terminal strip is bolted to the chassis. 2 capacitors? Let's take a bit of a closer look. I'm going to switch to another camera here, which may or may not have its autofocus on. Let's see how this goes. So we want to look right down in here. You can see the rivet and the somewhat poorly soldered connection there. So we've got two capacitors riveted to the chassis, two of them. Okay, that's not quite what I expected. Maybe there's more involvement here with the chassis than I realize. Let's keep going with this camera. Let's just zoom through the whole thing here quickly. This is the one I thought might be grounded, but it's not. It's connected to this. Looks like another terminal. What am I looking at here? Looks like another grounded terminal. I'm going to tip this and look. No. 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 Lots of wire. Almost all the wire is insulated in this radio. It's a little hard to look at up this close. Just yell when you see something that's tied to the chassis. Just shout it out. That's the volume control there. There's a capacitor way down there. Ooh, close to the chassis, but not tied. Oh, okay. So well, this is just a band holding this big filter capacitor here. You notice the radio didn't seem to hum. Well, a lot of rough shape there. It's really, and just look at the resistor there. You gotta wonder how much moisture these things have soaked up. Maybe they've soaked it up and dried out again. Looks like this radio was in some location where humidity was high, uncontrolled, like a garage or maybe somebody's basement. Somebody's too moist basement. Well, I only see this. Let's go back down and look at it again. So, is there also a wire on there? No. No. Just two capacitors. Why two? Okay, so one of them is this one. And that's a 0.025. That's not the size that we're looking for, and it looks like hard to see where it's going down towards the tube. The other one, I'm not going to see the size of it. Ooh, where's it going there? So I'm pretty sure it's that black thing going off to the left. That's just an insulating cover, and it's going straight to a tube socket terminal. Okay, back to the other camera here. So how do we end up with two capacitors tied to ground? I didn't see that in the schematic. Why would that even be? Generally, what you're trying to do is make sure that the metal chassis isn't just a piece of metal floating in space around all these radio parts, because it can act like an antenna, and it can also act to convey signals around the radio accidentally. We don't want those things, so what they do is they tie the chassis back to the B- part of the radio circuit with a capacitor. The capacitor's sized so it's small enough that if you were to touch this and ground yourself and set yourself up for a shock, depending upon how the non-polarized plug in and whether the switch is on or off, the shock you would get would be limited by the small capacitor. That's not a particularly small capacitor there. 0.025. Okay, let's look back on the schematic and see if we can find what I missed. I must have missed something. Let's go. So we found this. Now is there another ground symbol? Way up here. Now that's a shield. So it's basically another floating piece of metal that you don't want. Here's one here too. So these tubes have their shields grounded. You notice this one also has a shield, but they don't show any connection to it. And that's because the signals inside this tube, the output tube, are so strong and powerful that a little bit of nonsense from the metal shell here doesn't mean anything. You're not going to hear it. Well, those there's a capacitor right there. That's interesting. Why? And this got to be the other capacitor, 0.05, and the one down here, 0.025, the same one I saw. Okay, so there's the two capacitors. Why are they doing this? Why are they putting a capacitor here? Wouldn't you just shield that solid, or connected solid? Look at this. This shield. There's a wire going over to this shield. So all three metal tubes have their shields grounded, but these two are through a capacitor. Now that's a fairly big capacitor there, 0.05. Don't know why they do this. Don't know why. What would it be? There's some DC on here? How could there be DC on here that they're trying to block? See, I don't know. No capacitor in here. So I don't know. Don't know the reason for this, but it's there, and we found it in the radio. Now, if this guy is shorted, and if you've plugged it in so the live side of the power is connected here, then nothing bad would happen. It's this one that we would really worry about. If this guy were to short, which is not very likely, but if it did develop a short, or if it became so leaky, so conductive, then the chassis could be essentially connected to the live wire. I mean, you can see it on this schematics right there. So plug this guy in, and the metal chassis is now 120 volts, ready for you to touch it. So, but we wouldn't want that. We want this capacitor here. Still, it might still measure at 120 volts, depending upon the kind of meter you use, and depend upon which way the plug is stuck in, because it's non-polarized. What is that guy? What is that? Where's the on? Is this the on-off switch? Where is the on-off switch? I mean, it's on the back of the volume control, but schematically it's not there. This must represent a switch. The on-off switch. 14B and 14. So that's what this is. So 14B is the switch on the back of the number 14 volume control. Okay. Okay, so once again, so we would go after this capacitor because it's a danger. And we want to test this. Now while the radio's on my bench, plugged into my bench supply, there is no earth reference. I have an isolation transformer set up, so some of the shock concern I'm talking about down here is not there while this is on my bench. Let's leave this capacitor and go test this grid. The grid on the output tube, 50L6. Grid number we don't know. I will look it up in my book. Okay, here's a 50L6. You can see there's quite a bit written about it in this book. like half a page for it. Beam power tube, and there you can see the pin arrangement, and the grid we're after is what happened to what's going on with my camera? Maybe have some dirt on the front of it or something. Grid number 1 is pin number 5. So we're going to want to look at 5. And right beside it, 4 and 3 are also high voltage. They are high voltage terminals, the plate and the screen. You can look at those too just to see what's on them. But really it's 5 we're after. 5. Okay. Now to do this we have to operate the set again. And we have to pick a meter. And just for fun, let's try this. Let's try this meter. Now, this is new to me, this meter. I have a wire lead here with breaks all over it. I got to be a little careful with it until I fix it up. And you want to put this onto the B minus, not on the chassis. I've got to get it onto the B minus. Where's that going to be? So if we look at the filter capacitor, the black wire coming out of it, and that black wire disappears from view. Phooey. Phooey on that. It really does. You know what? There's a wax capacitor way down there too. So this wire here is taped, and they've used friction tape, which, by the way, is active. In Canada we call it hockey tape. The friction tape is actually much better than your standard electrical tape, which I'm just gonna. I see I don't have in my shop at the moment. The electrical tape tends to unwind, tends to come loose. This friction stuff I've seen. This is older tape. Stays. Now, the question is what's it doing in there? It may have something to do with this. This may be a replacement. The radio's not humming. Fat chance this can be original, but maybe it is. Hard to say for sure. But typically, in a radio like this, during its early life, maybe after 5 or 10 years, this capacitor gets changed. Maybe after 10 years. So there's a good chance of that. I need a hint as to where to pick up the ground, not the chassis. Well, the other end of this capacitor. The other end of this capacitor shows it. So I could hook it right here. Radio's not on or plugged in. Ooh, that's a tough spot to get to. Is that really correct? Watch it, man. You're going to bend this. You're going to bend the plate there. Absolutely, positively see it. Can I catch it here? Not really. Phooey. Okay, that's good actually. That made a good connection there. So that's the meter negative hooked up to B minus. What are we expecting here? Put this on positive. Again, I'm new to this meter. And what we're expecting to read is 0. That's what we're expecting to read. I'm not going to read a negative voltage here. I'm going to read 0 or a positive voltage. 30. This is an electronic meter. There are circuits and amplifiers driving the pointer. It's like a VTVM, only it's not vacuum tubes. It's a solid state VM. So it would be SSVM, but I've never heard that term used. Okay, that's one lead ready. Now the other lead, we're going to want to go across. Did I find that? pin number 5. Right. Okay, so that's this tube here. Yeah, pin number 5 in there. Right. Oh my gosh, it's all covered up. So we're going to have to try and use a tube extender here, I think, on this tube. What a dirty mess. So with a tube extender, I'll have access to all the different there. So here's my fancy tube stuff right here. All these terminals that I can access from above and not have to worry about it. Now we're looking from above, so we count the other way. So I often forget 1, 2, 3, 4, 5. So it's 5, 4, and 3. So that's grid, plate, screen. Tube won't fit anymore in here. There we go. Okay, that's in. Okay, so practicing, we would go grid. Expect to see 0. Plate, looking for 120 volts, and screen also 120 volts, something like that. We're on DC. We're flipped to DC. We're set on the DC side. And we're ready to go. Okay, I'm all set. All set. Come in. Okay, I'm going to apply power through the dim bulbs first. Because I'm a chicken, maybe I'll leave them in. Something should short out in here big time, like the rectifier tube, short right out. What will mainly happen in my shop is this light will get very, very bright. Nothing more will happen. Okay. Running with 100 volts or just under. Any voltage on the grid. See, there's a positive voltage. 3 volt scale. Almost 3 volts positive on the grid. That's bad, 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 bad. Now, we'll check the plate voltage. Did it make it over 100? Plate voltage is low. That's 60 volts there. That's pretty terrible. And the screen should be the same. The screen is much higher. Bad, that's bad, 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 bad. Could it be because of this grid problem? Interesting question. You don't want the screen higher in voltage than the plate. Except under very exceptional circumstances. I don't think this is one of them. Let me check again just to make sure I got this right. 50 L6. And I'll tell you why you don't want that grid to be positive. 50, Jim. 50 is bigger than 35. 50 L6. Again. So I got it backwards. So it's grid, screen, plate. Grid, screen, plate. Okay, so the plate is up around 80 volts. That's still pretty low for a radio like this. Could be low because of a couple of different reasons. You don't know which one it might be. Resistor gone high, could be the rectifiers dropping too much voltage, could be I don't have the radio operating on enough voltage. That's what it really is. Let's try this again. We're going to give it the full, almost the full Monty here. Okay, let's repeat. Rinse and repeat. So that's the screen up around 70 volts. That's the plate getting closer to 100. And now I bet you the grid has also gone up. So that's about 3 volts positive on the grid. It's bad. Now, we can get at the bias voltage, which will hint at the condition of that resistor. If I would just only stop closing my book here, keep the page, 50L6, 50. I should keep the book open. Here we go. 50L6. Cathode is on pin number 8. We should be looking for 5 volts. Ooh, I closed the book again. Oh, I'm stupid. Come on, Jim, don't close the book. What kind of grid? Grid number 1 to plate. No. This is capacitance. Volts. Typical operation. Grid number 1, control grid voltage minus 7.5. So we're looking for something around 7 volts, 7.5 volts on, oh, for crying out loud, 8, pin 8. So if we were counting these, this was 5, 6, 7, this is 8 here. We're on the 10 volt scale and we're looking for something like 7. And there it is, coming up right on 7. 7. A 4. A 7. Okay, you won't know what I'm referring to there, I'm sure. So we got to get rid of that capacitor, the one that's doing blocking the grid here, because it's not blocking it. So power off. Okay, let's see if we can spot that guy. Where is he? So we're talking about this pin. We're talking about, looks like this capacitor right here. Absolutely sure of that? Yeah, I think so. Let's be a little more sure. Try my meter out here. So we want to look and see if there's a continuity between, oh, I gotta stop for coffee, that's for sure, between pin, I forgot what I'm doing. Duh. Right in the midst of it all. What was he gonna do? You gotta look for making sure the pins were lined up here. Yeah. Okay, just want to make sure what I think is. Yeah. Okay, so this pin, this capacitor is the guy, 0.02. 0.02, huh? Let's take a peek on the schematic again. 0.02 blocking capacitor. 0.02 blocking capacitor. So I'm going to change that capacitor with a brand new one. We'll test this one and see how leaky it is, because I think in a sense we've already done that by finding this pushed positive a little bit. Let's find out. This is great. There's a good chance to get some insights into things. So I'm going to change that capacitor. I'm going to drink coffee and then change that capacitor. Would you believe the sun is shining outside now? So what I do myself, because I find I forget these things so quickly, or I get interfered with while I'm working, is I put a clip lead onto the terminals that the capacitor is connected to. And I've already cut it free from up here. Come on, here we are. If you've done a lot of this, you know what I'm talking about. You reach in to cut one wire and you cut two. Here he is. 0.02. Here's my replacement. It's an older capacitor, but it's in good shape. I know that. I have a bunch of these. So just thread it up and grab this. here. There we go. Now the other side. Okay, that's good. That's okay. That'll do. That's better. A lot better for working on it. Yeah, I can see much better now. This one over here. I took the clip lead off. Pretty sure it's that terminal there. Pretty sure it's good enough. It's going to have to do. Pretty sure it's going to have to do. There we go. Excess wire. So I've taken to not showing myself replacing capacitors, but I'm showing you this one. There we go. It's on the terminal there. It's on the terminal up there. Nothing is shorting. Okay, I'll solder that up in a minute. You don't have to watch that. Let's watch what happens here. Oop, where am I going? So this is a capacitor tester designed to test, capacitors of old capacitors. So, so this looks to be in really good shape. This capacitor, a little dry maybe here. I'm looking for the separation of the end here from the. No, it's in pretty good looking shape. Interesting to see. The other test says it leaks. Let's see what this one says. Now in the radio there's probably 50, 60, 70 volts pushing on this. And this tester the first test, put in the right spot, is 50 volts. So we're going to push 50 volts across here. And then the current leaking through it or going through it will close this eye. If there's no current, the eye is open like this. If there's a leak, the eye may close and not open at all. That it should close momentarily while the charge current flows. Here we go. And look at that. So now you're having a hard time seeing it, but it's open only a tiny amount. So as capacitors go, in these old radios, this one's definitely on the badder side of bad. Definitely. A bunch of old capacitors from other radios. Put them in my dead soldier box. So, okay, now we have the new guy in. I haven't soldered them. I'm going to solder them in. And then we're going to try the radio again. I'll repeat the measurement of the grid voltage and see if I haven't cleared up that problem. Did I explain what the problem is? If you let the grid go positive, then the grid itself will take current. But more importantly, it will encourage a heavier and heavier flow of current through the tube. What this does, it heats the tube up further. Depends how serious it is. You can get it hot enough to make the tube plate glow red. That would be very bad. But the excess current will wear out the cathode faster. And the output tube's already working hard. It's already got a shortened life. These radios are designed that way. A shortened life relative to the regular signal tubes, which aren't working all that hard. And a positive grid is just going to make it work that much harder and wear out that much sooner. Okay, I'm going to solder that guy in before I forget, and we're going to test this guy out. He's a guy. I can tell. I might as well watch everything that happens here. I'm going to solder this guy in. sometimes when I'm after one capacitor, there'll be others in the way. As much as I'd rather do this in a very planned way, I end up changing the ones that are in the way because it's just too convenient to not do that. Then that kind of disrupts the chance to complete the experiment. Okay, that's sorry there. The experiment being, can you really get rid of? Did I not squeeze this down? No, I didn't. I did not squeeze him down. So quite often I'm trying to do things in such a way that it'll reveal something to me. I'll learn something from it, but then part way through the process, it goes sour because of other factors, uncontrolled factors and things like that. So in the end, you're not really 100% sure about the effect of what you've done. I like, this is an opportunity for me to learn about this stuff, so that's why I take that course of action, and I find learning fun. Isn't learning fun? Wow, this school really, you know what I say about school? School is interfering with my education. That's what I say about school. As much as you're learning things in school, you're also maybe learning some bad things. Like I learned at an early age I can't sing. Well, that's not true. Anybody can sing. Everybody can sing. If you want to take some time and practice and learn to do it. But I was convinced by grade 2 that singing's not for me. I missed out on that in life. Had I thought I had some ability to sing, I probably would have sung more. So here at this point in my life, I have taught myself to sing, but I'm not going to demonstrate it because I'm not good at it. Okay, we'll put this back down. Now find out ground at B minus. The word ground is just so misleading. It's abused here in North America, something terrible. You notice the Brits like to use the word earth. That's much better. You know, even terms like volts and amps, they don't tell you anything. I had this old document when I was working at the power company. Very old document from about 1910. And as a technician describing work he was doing on the transit system, streetcar system at that time. Just streetcars, running on tracks in the road. And his report said he'd gone out to such and such a location to check the pressure between the rails. And I read that, whoa, check the pressure. What? But pressure? Well, he's talking about voltage, but the word voltage wasn't used then. He used pressure. But pressure is a much better word. Voltage doesn't tell you anything, but pressure gives you a hint as to what it is. Voltage is pressure. Check the pressure between the rails. I'm not exactly sure why he was doing that, but the rails form the part of they form the return circuit, if you can put it that way, for the power going through the streetcar, right? It comes from the wire above, down through the motors, and then into the track. The tracks are conductors, and they need to be maintained. And since the streetcars are going over them and the tracks are shifting and that, the connections, the continuity of the track can fail. Big problems ensue. Okay, enough of that. We're not fixing the streetcar here. We are fixing the radio. So I want to repeat the grid voltage measurement. Just making sure I don't have a clip lead where I shouldn't have a clip lead. Ready again. Volume down. So conceivably now, the output tube will be a happier camper in this radio. But let's find out. So put this back down here. You can come down. Come down. Come down. Get a better look at the voltmeter. 3 volts last time. Is Jim full of crap? Or is he telling the truth? We're going to find out. Seems like a little more volume there. Well, we're hearing a hum now. I didn't notice this before. The volume's right down and we're hearing quite a hum come out of there. You see the meter? Not, is it moving? Let's put it right down on, oh my gosh, it goes to 0.3 volts. Wow, okay, 0.3 volts. It's picking up a charge. So now watch this meter very carefully. When I first contact the grid over here, the meter will go up and then it will come down. Here we go. So what's happening there, I would say, is the meter is drawing a charge off the grid. The grid is still going a little bit positive. Now we're on the 0.3, right? So we're talking about a tiny voltage here. Well, how do you explain that, Jim? It just went the other way. Or maybe something to do with this meter. In any case, we're not looking at 3 volts here anymore. I rest my case here. We are in good, much better business. Let's just check. Did the plate voltage change? Would that cause a plate voltage change? The plate was 70 or something like that. Well, maybe it's a touch higher. And then the screen, or if I got it backwards, that was the screen. This is the plate. 90, it's higher. Why would it be higher? It would be higher because the amount of current flowing through the tube has been reduced. The quiescent current, if I can call it that. Or the steady state current, maybe you can call it that. It's been reduced a bit. And that's less current, less voltage drops in the plate circuit. So more voltage available at the plate. So getting up around 100, that's kind of where you want it. And see, right now we're running a little low, 106. Let's put it up where it should be. It should be 117. Now I'm still forcing the current through the dim bulbs. So on the other side of the dim bulbs, the voltage is much higher than 100. 115 now at the outlet here. 115. What do we get now? Screen, almost 80. Plate. Well, we've made it to 100 volts plus. And grid. 1 volt scale. Grid. You can hear it come out of the speaker. Why the change in the sound on the speaker? Oh! Oh! I just touched the chassis for no good reason. Of course, I'm on the 1 volt scale here. Not sure what that would mean. Not sure about that. It's plugged in an isolation transformer. So that's it for today. Great! Okay, I think we're well on our way to making this radio work. And that's good. Very good. You know, there's a lot of people around who would like to refinish old wooden radio like this, but they don't know what to do with the insides because they don't have, you know, all this stuff to help them. So I don't like doing the cabinets. I don't like the woodwork. I should find a partner. Okay, remember, turn that off. Don't forget. Very good. Thanks a lot for watching, and tomorrow we'll continue doing some more capacitors and more poking around. See ya.